Ask not what you can do for partial fraction decomposition. Ask what partial fraction decomposition can do for you. Let's talk about how we can use this technique to actually get the antiderivative of a variety of rational functions. For example, this one. Let's integrate 1 over x squared plus 3x plus 2. And up to this point, we still don't have any techniques to actually integrate this function. Substitution, trig substitution, integration by parts, none of these techniques will work. So let's try a little technique here of first factoring the integrand. Factor it. So not x squared plus 3x plus 2. Let's think of this as x plus 2, x plus 1. Now the integral behaves very nicely with sums. So I wonder what would happen if we took the integrand and we broke it down as the sum of two simpler rational functions. One with a denominator of just x plus 2 and one with a denominator of just x plus 1. Now these being linear denominators, degree 1, is going to have a degree 0 numerator. So I'll call it a and b. And now, to find a and b, let's go through and clear the fractions. Now we are somewhat lucky because both of our denominators here have values of x that will make them 0. So let's try this trick of plugging in a value of x that will eliminate one of these factors. Let's set, for example, x equals to -1. If I do so, I get 1 equals a times -1 plus 1, b -1 plus 2. And if I do that, I will end up with a times 0, so that's gone, b times 1, and therefore b itself must be 1. Now I can use the same technique to find the value of a. Not by setting x equal to 1, but by setting x equal to -2. This will eliminate the factor that's next to b, and I will get 1 equals -2, a -2 plus 1, so a is equal to -1. Alright, now that I've given myself a little bit more space to work, let's go ahead and let's put this information back in and rewrite the integrand with our new knowledge of a and b. The thing that we're actually trying to integrate here, the integral that we're actually trying to find, can be thought of as a equals -1 over x plus 2 plus b equals +1 over x plus 1. But now these rational expressions are so simple that their antiderivative can be found just by using the natural log function. The natural log arises, natural log absolute value of this linear x plus 2 plus natural log absolute value of this linear x plus 1, and then plus c, or our indeterminate arbitrary coefficient. So this is the upshot of partial fraction decomposition. It allows you to split apart a complicated rational expression into a sum of simpler rational expressions so that you can take their antiderivatives one by one. Let's try something similar here with the following rational expression. Integrate 5 over x squared plus 1 times x minus 2. So let's begin by trying to split apart this difficult antiderivative into a simpler antiderivative. Now x minus 2, being of degree 1, will need to have a degree 0 quantity above it. And x squared plus 1, being of degree 2, will need to have a degree 1 quantity above it, so something that's linear. So here I go to clear the fractions, and I find that 5 is equal to a, x squared plus 1, then bx plus c is multiplied by x minus 2. Now, can you think of an x value that might be convenient to plug in to this equation? I think I would try x equals 2, which will cause this entire back term to vanish from 2 minus 2. And I get 5 equals a, 2 squared plus 1, and therefore a must be equal to 1. Having found a, let's go and try and find b and c. We have 5 equals 1 times x squared plus 1. Let me just highlight this for emphasis. Then bx squared, then negative 2 times b times x, then c times x, then negative 2 times c. Now let's have a look at what's going on with the x squared type terms. I have x squared plus bx squared, but I have no x squareds on the other side. So I think that means that 0 must be equal to 1 plus b, which seems to mean that b is equal to negative 1. We can also look at the x-type terms, negative 2bx, cx, but no x's on the other side. So that means that 0 is equal to negative 2bx plus c. And using the fact that b is minus 1, I can find that b times negative 2 is equal to positive 2. So c is equal to negative 2. Let's highlight that as well. So what integral am I actually taking? I'm taking the integral of the following. I'm taking the integral of the quantity a, which is 1, over x minus 2, plus negative x, negative 1 for b times x, minus 2, over x squared plus 1, which can be broken down even further as 1 over x squared, 1 over x minus 2, minus x over x squared minus 1, minus 2 over x squared plus 1. Now, each of these three individual rational functions has the format of something whose derivative we've already found. For example, here would be the natural log of the absolute value of x minus 2, as a consequence just of our regular ordinary natural log formula. We can use u substitution on the second term to find that this must be equal to 1/2 natural log x squared plus 1. U substitution with u equals x squared plus 1. And this last term has exactly the format of inverse tangent. So this last term can be split as 2 inverse tangent, or arctan, of x, then plus c, and this will give us our final answer. Breaking down a complicated rational expression into a sum or difference of much simpler rational expressions whose antiderivatives we already know how to find. Now, just a word of warning. Partial fraction decomposition, as we have done it, is a process that can only be applied if your original rational expression has a degree in the numerator that is smaller than the degree of the denominator. For example, the degree of this denominator is 3 from x squared times x, giving you an x cubed. And the numerator has a degree of 0, which is significantly smaller than 3. But we're going to have to employ a different technique in the case that I had, for example, 5x to the 4th power in the numerator. We'll see that we can use a process called polynomial long division to help with such a problem.